Hi, my name is Matthew Cowell, and I will be presenting our CVPR paper on quantifying static and dynamic information in deep neural networks. Deep spatiotemporal models have been shown to be effective at various tasks such as action recognition and video object segmentation. However, there is a limited understanding of what information is captured by these models in their intermediate representations. For example, it's been shown in previous work that action recognition algorithms are biased towards appearance information, and strong performance on certain benchmarks can be achieved using only a single frame. In this work, our goal is to design a metric where, given a spatiotemporal model trained on a given dataset, we can estimate the static and dynamic information contained in the model. To show the efficacy of our approach, we evaluate on two popular video understanding tasks: action recognition and automatic video object segmentation. The overall approach has two parts. We first sample a video from a dataset and randomly select a factor f. Based on this factor, we generate a second video by performing either a static perturbation, which perturbs static information while keeping dynamics, or dynamic perturbation, which perturbs dynamics while retaining statics. These video pairs are passed through a pre-trained model f theta to produce representations z1 and z2. The second part of our approach is then to estimate the mutual information between the static and dynamic pairs. We then use the relative static and dynamic information as a measure of the model's bias. We now review the sampling procedure for the two tasks. For action recognition, the input is an RGB video, while for VOS, we consider two-stream models where the inputs are single frames of RGB and optical flow, as they currently show the strongest performance. To construct the dynamic pairs for both tasks, we use a recent video stylization approach and generate two different styles of the same video. For the action recognition static pair, we temporally shuffle the frames of the same stylized video, while for VOS static pairs, we use the same styles in the RGB stream but perform color jittering on the flow. Now we estimate the mutual information between pairs of videos. With the assumption that the joint distribution between the two representations is Gaussian, previous work has shown that the correlation coefficient can provide a lower bound of the true mutual information. We use this bound to motivate two metrics. First, we define a metric that allows us to quantify the static versus dynamic bias in a model on a layer-by-layer basis. Second, we define a complementary metric that allows us to quantify static versus dynamic versus jointly encoding units on a unit-wise basis. Full mathematical details are provided in our paper. Now on to the empirical results. We first explore architectures in recent state-of-the-art action recognition models. The layer-wise metric shows that all models are biased towards the static factor at all layers, which can be seen by the uniformly higher scores for static compared to the scores for dynamic, except for the last layer of the slow-fast model's fast branch. The unit-wise metric shows that all models solely produce static and joint units apart from the fast-only and fast branch of the slow-fast model. For VOS, each stream is biased towards its corresponding factor at the last layer. The unit-wise metric reveals that both our TNet and FusionSeg produce mainly joint units, while MatNet has a more even distribution of static and dynamic units. Looking at action recognition datasets, we found that models trained on Diving 48 encode a similar amount of dynamics as kinetics. To confirm this finding, we train models on videos with shuffled frames and calculate the relative performance. We observed that SSV2 has a much larger drop than Diving 48 in kinetics, suggesting it is a better dataset to use to evaluate a model's ability to encode dynamics. For video object segmentation, we observed that tau VOS produces the largest number of dynamic units compared to Davis and ImageNet VID. We also visualize heat maps of the average ground truth segmentation map for each of the datasets, and can see that tau VOS is the least center biased dataset. Together, these results suggest that dynamics bias training should be conducted on tau VOS. Finally, to measure the effect of static and dynamic units on performance, we perform validation while zeroing out the top K dynamic and static channels compared to randomly selected channels. For the slow-fast model in SSV2, we observed that dynamic units reduce the performance significantly more than other units, while for the task of segmenting camouflaged animals, static units produce the quickest decrease in performance. In conclusion, we have introduced a new metric for quantifying the static and dynamic biases in deep spatiotemporal models. We confirmed that most models are biased towards static information. We then ranked multiple datasets in each task based on their biases, and finally we showed the large impact of performance of static and dynamic units on downstream tasks.